Okay, let's get now we have Big O. A brief understanding of Big O. Not a lot. It's not. It's just man, find a loop and then see if it starts at 0. If it goes all the way through, it's O to the n. If you have two loops, it's n squared. When we get into our binary, our divide and conquer algorithms, we're going to start getting into the log n and n log n stuff because we're dividing by 2. So, and that's what we're going to do today. We're going to do some sorting and searching. And these are kind of the starting points of what you need to do. We'll get sorting and searching out of the way, and then we'll start with our linked lists and that sort of stuff, kind of get into this thing, how it gets going. We get the linked list done. And most of our data structures are going to have some sort of relationship to a linked list. Trees, hashes, graphs could be, it could be in an adjacency matrix or an adjacency list. But we'll get into that. Let's just jump into sorting and searching and talk about a couple things that are really important. And I'll have some code for you, and I'll have a copy of the code in links below, so you can just grab, copy, and paste and play with it. And I'll show you some stuff. Okay, here we go. A little bit of a warming up to an array. You know, we just want to implement sequential and binary search algorithms for an array structure. And you've already done sequential searches. We're going to introduce a binary search, and we're going to implement iterative sorting algorithms for array data. Okay, so just some stuff that you're going to need to know as you move forward in your computer science and software development pursuit. Okay, there are a lot of built-in sorting algorithms for you to use. Okay, we're going to write our own sorting algorithms. We're just going to go over some sorting algorithms. These are basic sorting algorithms that run at a pretty inefficient speed. They're n squared, so they're going to be nested loops. And we're going to show you, I'll show you how to do a text file and add strings, and so that way you can have a text file and populate your data structures from a text file. It makes it faster than just trying to do it typing in an array and typing in a whole bunch of words. We can just copy, grab 100,000 words or 1,000 pieces of data and introduce it into a text file, and then we can populate our data structures, and that gives us control over n, right? The amount of stuff that's going into our text file that we need to work with. So with that, we're going to look at, after an array is created, we're going to build a bubble sort, insertion sort, or a selection sort, and this is going to alphabetize our list or sort the array. And you can use whichever one. I'm going to go with the bubble sort. I'll show you the bubble sort. I'll show you all three sorts, but I'll code out the bubble sort for you. Okay, somewhere it's capitalized, you just get that. So if you're not dealing with capitalization like ignore case or to lowercase, you're going to capitalize letters are going to be before. So capital zoo is going to come before lowercase apple. And then we're going to do a binary search on that list. So we're going to get a list, we're going to sort it, and then we're going to do a binary search on it. All right, pretty fun stuff. Let's get going. All right, what's the difference between a sequential versus a binary search? Well, this is something we need to know. Simply put, a sequential is having a linear relationship. An array or list, all the elements have a linear or sequential relationship. That shouldn't be too hard for us to get a hold of in our head, right? If I have an array, now again, these are abstract data types, so the array, well, I guess it is, because it's a continuous block of memory in C++. And we kind of deal with that in Java too. So this is an array. It starts at 0, 1, 2, 3, 4, 5, 6, and goes to 7. And then we put data in here, right? This is just data. So we have data in here. Now, it has a linear relationship. I know they're indexed, and if we grab an index, that's O to the 1, because we're just knowing where we need to go. But if I want to start at 0 and get to the very end and print everything out, I have to go through the array, right? 0 to 1 to 2 to 3. That's a linear relationship, one after the other. If I'm searching for a number 2, I don't know where 2 is, so I got to start at 0 and go find it. And that's a linear relationship. A binary search has an advantage over the sequential search. First, you don't think binary has anything to do with taking down to the bit level. This is not like a bit level binary search. I put that in there because I had a student email me. I'm trying to do a binary search and I don't know how to turn all of my data into bits. And I'm like, no, not that binary. Binary means 2. right? In a binary search, divide the array in two and search that half. Sequential starts at 0. A binary search starts in the middle. Okay? So we're going to do a binary search. I'm just kind of jumping into this when we start doing some things. Okay? So binary search starts in the middle, and then we decide we cannot do a binary search on unsorted data. All right? That's really important to know. We can't do a binary search on unsorted data. Binary search works with sorted data. So we're going to sort our stuff first. Okay? So we're going to come back to this as soon as we have a sorted array. This, of course, is unsorted. So let's get into that. So we're going to write a method that implements bubble sort, insertion sort, or selection sort. I'll go through each one of them. The sort you use is up to you, but you got to write it. You can copy and paste mine. For the bubble sort, it bubbles to the top. So a bubble sort is called bubble sort because it bubbles to the top. It finds the largest number, and it just keeps comparing it on the indexes until it gets to the end. So as soon as it finds the largest number, it does a comparison of one index to the next index, one index to the next index, one index to the next index. If you took my earlier class, we did a lottery picker where we sorted our data and we had to find duplicates. And we just ran a loop that was I and j, and it just compared each index. And if it found a duplicate, it ran over. Now, after this class, you'll know about trees and map sets, and you can just do that without the linear search. Okay, but a bubble sort, bubbles to the top. This sort starts at index 0 and compares the value of the next element until the smaller one, if it's smaller, then there's a switch. It continues until the element up is larger. Once it hits a larger element in value, the bubble sort keeps moving that element up. So, visuals, let's look. Okay, if I look at this as a single number, this is sorted. If you think about it, right? 54 by itself is sorted. That's pretty cool. Any single value, any one value is sorted, and that's important when we get into our merge sorts. So if I have I can alphabetize a single number or letter, right, or a word. I can if I get one thing, it's always sorted. Okay, so 54 is by itself sorted, but if I compare 54 to 26, well, look, 54 is bigger than 26, so 54 is going to bubble up. Now this is one pass. So there's now 54 is the big number. 54 compares to 93. 54 is less than 93. 26, 54, and 93 is sorted. That's all sorted. Well, 93 is bigger than 17. So we're going to need to make that switch. So 93 switches with 17. Now 93 is bigger than 77. So 93 and 77 are going to switch. 93 is bigger than 31. 93 switches. 93 is bigger than 44. 44 and 93 swap. 93 is bigger than 55. 55 and 93 swap. 94 is bigger than 20, so it swaps. This is after one pass. Now we're going to have to do the pass again. 26 and 54 are sorted. 54 is bigger than 17, so 54 will swap with 17. And then 77 will grab it, and 77 will swap all this way up until it becomes here. 77 is less than 93, so it stops. We come back, 26, 17, 26 and 17 will swap, and so on and so on and so on. That's our bubble sort. Okay? The selection sort is an improvement on the bubble sort. It will select the largest number and place it to the appropriate space. So bubble sort bubbles up, selection sort selects the number and just moves it across. Okay? It only makes one swap per iteration, meaning when I loop through my nested loop, it makes one swap per nested loop. Like the bubble sort, after each pass, the largest item is in the correct place, but it swaps indexes. So let's look at this really quick. This is my selection sort. Here, I got 26 and 54. I know my largest number is 93. So I take, and 93 is going to end up at 93 is the largest. So I'm going to go up here and I'm going to go to the end and I'm going to swap it with what's there. Okay? Because I got to keep my data. So I'm going to swap 93 and 20. Now 93 and 20 swapped. My next biggest number is 77. So 77 and 55 are going to swap. My next biggest number is 55. 55 and 44 swap because it has to go this way. Now it's always going, since we got 93 as the biggest, it's always going -1, right? From where I was, -1. So that's my swap position. Now I've got 55 is in place. 54 is less than 55 but bigger than 31, so I'm going to swap it. Right? You're like, hey, how did it know that? Well, 54 is less than 55. So 44, well, that doesn't need to swap anywhere because it's the next biggest number. It's in place. 44 is less than 54 but bigger than 17. 31 is less than 44, so 31 and 17 are going to swap. And then it comes to here. 26 is going to swap with 20, and then 20 is going to swap with 17, and our list is sorted. This runs also at O to the n squared. It's going to run with a nested loop, and I'll show you the code. And you'll say, oh, it's a nested loop. So we have n times n squared, O to the n squared for bubble sort, O to the n squared for selection sort. Okay, let's go to the other one. And this is the insertion sort. This is another n squared. This works that shifts indexes. Okay, it doesn't swap indexes, right? Like the selection sort, it shifts indexes. It inserts it in place and moves the index over. Insertion sort keeps the sorted items at the lower end of the array and will shift unsorted items to the next index. As it happens, it'll compare the shifting values. If it's lower, it'll shift the index to the right. When it finds the correct space, it drops it into the empty index that is vacated by the shifting index. Think of this as being able to take one peg out and make room for the other peg and sliding it over. It's kind of like the towers of Hanoi. This is n squared, like the bubble sort, and selection sort. The thing is, it's a little easier on your processor, resource-wise. Okay, it's a little hard to visualize, but let's take a look at this. Okay, best thing to think of is shifting the index over to make room to drop it in. One thing about this, shifting indexes uses much less processing power than exchanging indexes, which was a big deal back when we had very small resources to work with. Okay, now assume 54 is sorted in a list of one item. We talked about that. Every single item is sorted. Now I'm going to insert 26. 26 is inserted, right? Because 54 is bigger than 26. So 26 shifts over and 54 goes into place. Okay. Now, remember, we're keeping everything, the bottom part is always going to be sorted. Okay. So 26, 54, and 93 is sorted. Well, that's not good because 54, we get to 17, right? Now we're going to add one and we say, where do you get into this? So we're just keeping the bottom part sorted. This is sorted. And then we check the next item and we say, okay, what are you? You're like, I'm 17. Like, you're 17. You're the lowest number we have. We're going to move over and we're going to drop you at the beginning. Now look, this is sorted, 17, 26, 54, 93. We add one more value, 77. 77 fits between 54 and 93, so we shift 93 over. If you look, this array is sorted. It says, oh, hey, 31, where do you go? Well, 31 is less than 54, but greater than 26, so we're going to shift you guys over and we're going to drop 31 in. Now all this is sorted, right? And then we get 55. Okay, where do you go, 55? You're bigger than 54 and less than 77. So we'll shift over, and then we find 20, and it says, okay, where do you go, 20? And it says, I am bigger than 17, but less than 26. I go there. That is our sort, okay? Insertion sort. All right, what do these look like in code? Well, in Java and C++, sorting the array, things get to be moved around a lot and swapped. In order to do this, we make a temporary variable to hold the extracted values, right? We got to hold that value, move stuff over, and then put the value in, either the bubble sort, the insertion sort, or the selection sort. We need to take that value and store it in another variable so that we can reinsert it into the array. Okay? In a simple bubble sort, you compare the first element with the one next to it. If the current element is greater, it's swapped. We're going to use a nested loop. Nested loop, we have a for loop and another loop inside of it. Okay, usually a for loop, but we use a while loop for the insertion sort. Let's take a look. Come on, it's fun. All right, this is, of course, we're at the C++. This is my bubble sort. Here's an unsorted list, right? I have a temporary variable called temp, and that's given a value of 0. And I just print out my loop. I just print out my thing. So that's the output right there. Unsorted list. Okay. Now I know it's size 6. Okay. And then I have my first for loop. So if my array was bigger, this would be n, but it's 6. So this is my first for loop. And then this is my second loop. Notice I started I at 0 and j at 1. Well, what's that do? That keeps me in bounds. I'm taking I here and j here. And this gives me the opportunity to compare one after the other. Okay? If j minus 1, well, this is j minus 1 is 55. If j minus 1 is greater than j, well, j minus 1 is 55, j is 20, that's greater. Temp is going to equal 55, right? Now we got 55 held here. And then the index of j minus 1 is going to equal j. Look, that swaps. J minus 1 is going to be 20, and then j is going to be 55. That's my swap. That only happens if the number is bigger. So it goes through. Now this has to go through the iterate, or go through this list, or this array, 6 times 6 times. Okay? So this is n squared. Because it goes through, it comes back, it goes through again, it comes back, it goes through again until everything is sorted. So it has to touch each element every single time. And that's our bubble sort. Kind of cool. The selection sort is similar. Okay? The subarray is sorted, and that's the lower array. The upper array is unsorted. When we talked about the selection sort, remember that we just get the first element is always sorted because it's by itself. Then we compare it to the second element. If it needs to, it's going to pick it up, select it, and then move it around. And that's our swap. It keeps the comparison just like we did with the bubble sort, except it's got a little more flair to it. Again, array is built, let's call it foo. Anybody old school programmers know foo is what we use. Print it out, there it is, for loop, and then we're just going to do our index and then another for loop. Okay, again, j is going to be I plus 1. J is going to go 6 times. Okay, 6 times 6, n squared. O to the n squared. All right, you start getting this this big O stuff down. When you go to your class, you'll be a star. All right, if this is at the found index, which is I, we're going to select it over. And then we hold it. This is my holding, and then we do the swapping on this side. If lower number equals this at the found index, we're going to make the swap. And then I is going to equal lower number. So 55 is sorted by itself, and then, oh, we're going to make this swap. And then we go through the whole thing as that works. Kind of like the bubble sort, but we're doing a selection. We're picking it up when we're putting it into place. So 55 is just going to cruise all the way down, and it's going to get down to here, and it's going to move 10, swap with 55. That's all that does. It finds it, it's just going to keep moving it down until it gets to the biggest spot, and then it's going to plop it in. The next one it'll pick up will be 20, and it'll move down and it'll swap. Okay? Insertion sort, this is the shifting index one. Okay? Because this you need to start the loop at 1 and not 0, because 1's already sorted, right? The loop will look for an element that is lower than the next element. If it finds the lower element in the index, it is sorted in a temporary variable called the key normally. This is done with a while loop. And this is also O to the n squared. And I'll show you how we achieve O to the n squared. Not the most efficient, because we can write sorting algorithms that are log n. And that's awesome. All right. So that's going to be our key, and we're going to say, well, j is greater than 0, and array list j minus 1 is greater than key. Okay? Then we're going to make our shift. Okay? So let's look at this coded. And we have this. Here's our foo array. There's this printed out. And here we go. Here's our for loop, and here's our while loop. So our while loop is nested inside the for loop. So the for loop runs, the while loop runs its iteration, the for loop comes back and runs again. N times n. It's inside of the loop, n squared. Okay? This loop is inside of this loop. So here we do. Key is going to start at the foo at I. Well, I is 1, so key is going to start here on 20. And then it's just going to do its comparison. While j minus 1, right? J is I minus 1, right? And If it's greater, if these are greater, then I'm going to hold on to that and I'm going to make my shifts. Then the lower value is put into place and it comes back and does it again. So this just goes through, it shifts the value, it shifts the, keeps the lower order, this ordered, and then it just shifts the stuff across. So the lower part of the array gets sorted each time and everything shifts over one when you get a bigger number. That's it. Those are our three sorts. Those are the three learning sorts. They're all O to the n squared. Okay? And they're pretty cool. They're kind of fun to work with. They're not practical for sorting algorithms. I mean, maybe for a small array, the bubble sort's pretty cool. The insertion sort's pretty fast. Large data, no, not at all. Don't use them for large data. Well, you could. Just inefficient. It's n squared. You know, a lot of things run in polynomial. If we can avoid it, it's better. Good for interview questions too. And sometimes you get an interview question that says, hey, here's a list of unsorted integers. What will the list look like after 2 iterations of a bubble sort? And then you're just going to, in your head, you're going to be like, okay, I know what a bubble sort is. And then you're just going to say, this is what it looks like after 2 iterations. And your x2 numbers will be at the very end. That's your bubble sort. All right, there are a lot of algorithms that you'll be used to sort strings. The examples are working with integers in this right here. The examples I'm going to do are going to be in Java. And we're going to do a string array, and I'm going to show you the string array and how to get that to work and how to do a bubble sort and then a binary search on it. Now, you're in Java, and this is my biggest thing, even with people coming that have been programming for a while. They take a class in C++, they take a class in Java, and then they start using C++ to compare strings. You can't. Java string's an object, so you have to use compare to, and my favorite, don't compare my face. My favorite is compare to ignore case. Okay, so that way capital zoo is going to get at the end of your list because Z, of course, is a Z. And if apple is there, you don't want zoo in front of apple. That'd be silly. So remember compare to and dot equals for Java. Okay. So once the array is sorted, here's where we get into our binary search. Okay. Once the array is sorted, then we can implement a binary search. Now a regular search is going to run at O to the n, right? But a binary search, we get to cut the thing in half, so we never have to go through the whole array. So we're going to be in log n, which is cool, much more efficient. So we can have the user repeat, ask for more things. We're going to use our binary search. Okay, it's simple to do. Okay, so let's go ahead and take a look at our binary search and what it is. So a binary search, get the value of what you want to find. If I have an array, good thing I don't teach art. 0, 2, 4, 6. Now, you notice my array is sorted. Binary search won't work if it's not sorted. Okay, but let's say I'm looking for 10. So I'm looking for a 10. Now, a linear search, right, is going to have to start at 0 and work its way all the way across until it finds it at this index. 0, 1, 2, 3, 4, 5, 6. So it's gonna have to start at 0. But if I'm doing a binary search, I'm going to look for 10. So here's what I do. I find the middle. So this is the middle. Okay, we're just going to say that's the middle because, well, it is. And then I check the value. Did I find it? Is 6 10? And it's not. But what I'm looking for is larger than 6. Because it's sorted, I know that all the value to this side is less than 10. So now I only want to look on this side of the array. I cut it in half. I don't have to search the whole thing. I'm only searching half. Now what do? Well, I cut it in half again. So I'm only looking at this part of the array. This is no good. 10's not there. Now I only look at this part. So then I cut it in half. Depending on what your algorithm says, maybe you cut it in half and you get 8. 10 is greater than 8. So now I know it's in this part. And then I cut it in half and 10 is there. So instead of iterating 5 times to find 10, I did it in 2. That's faster. 2 is less than 5. And that's great. And that's what we do. Now, this can be recursive too, and we'll get to that later. But we're just going to keep repeating these steps. Find the middle, check the value. if it's lower, if it's higher, boom, boom, boom. It's pretty cool. All right, let's look at how we do this with our code. And I have this written out in Java for you, and I'll show you in Eclipse with some strings. So I know the size, because this is C++, so I'm just going to get the size. I know the size is 8. I'm looking for a 15. Okay, this, my friends, are sorted. So I just started with a sorted array. And all I'm doing is I print it out. And then I'm saying why I is less than length. So now I is less than length. Well, that's pretty cool. Length is 8. I, of course, is, where does it say? I is 0. So 0 is less than 8. Meaning that every time I work my length, it's going to work, I is going to work my way up to length. Then I find the middle. I plus length minus 1 divided by 2. That's going to be my formula for finding the middle of my array. Okay? If I found it, if what I'm looking for, let's say I'm looking for 20, boom, right in the middle. 20 is there. I found it. If not, if the mid is less than the key, then I is going to shift to mid plus 1. Okay? So if I'm looking for 20, let's say I'm looking for 25. 25 is greater than 20, so now I'm only going to search the top part. If I'm looking for 15, 15 is less than 20, so I'm going to search the bottom part. This is how I find my top and bottom. Then I go back, right? This while loop is running. There's no nested loop. It's just one while loop with a whole bunch of if statements. So these parts are O to the 1. This is O to the n. But because I'm dividing each time, I'm not going through the whole thing, not O to the n. It could be O to the n, but I'm not starting at 0. I've changed my loop invariant, and now it's O to the log n. And that's a binary search. Pretty cool. Super fast. All right. I'm not going to go into dynamic arrays. I used to have an assignment where you had to take a Java or a C++ array, and then you had to make a dynamic array, and that stuff has to do with like array copy and stuff like that. We'll get to that later. Let's just play with our searching and stuff, and let's just jump into some code, okay? Because we have array lists. When we get to our linked list, nobody writes. We have libraries for dynamic arrays. We don't really resize arrays anymore. You might have an interview question or elite code on it, but we'll figure it out. If you stick with me through the rest of these videos, one, you'll be sick of me. Two, you'll know how to resize an array if you need to. If you need to. Just plop it into an array list or a vector or a tree or something better. All right, so we're not going to do this. I'm going to skip that. And then what we're going to do is, you look up freecodecamp.org, big theta asymptotic notation explained. This is a really, really nice resource to find all the stuff on Big O, and it explains. It's very easy to read, very easy to overview. It's just it makes you really smart. So Big O, we're concerned with Big O because Big O is upper bound and Big O is worst case, right? Big omega is lower bound, and we have big theta narrow and big theta exact. And that's like if I know exactly where something is in an array, I don't need to loop through it. I can just go get it. All right, so let's go over and I'll fire up Eclipse and we'll go through some code and I'll paste those for you. Okay? All right. If you're pondering, consider an array of 100 integers, which are completely unsorted. Provide code snippet that finds the largest number in the array. Take some, after you get this and you play with some of this code that I give you, go ahead and write your own. I'll give you the bubble sort. Write the insertion sort. See how it goes. Write the selection sort. See if you can sort it out with the, change your sorts. Play with, do some output to see how many iterations you're doing. Stuff like that. It's fun. All right, let's get over to Eclipse and we'll show you some code. All right. Hey, super kids. Here we are. And I'm just to have a little bubble sort that I wrote. I'll put this code for you. But this is just a quick little bubble sort. It's in my little bubble sort class. I have a cute little method right here called bubble sort. And don't put those in there, you'll get an error. So let's just walk through it really quick. And I'll paste this code into a text file for you. I have my import my java.io. If you look, you can explore the other stuff that I have. I have my utility, and I included a thread. So we're going to thread this just so I can slow some stuff down, and that threading allows me to throw a sleep in there. So Here's my bubble sort. It's just what we did. I'm going to pass in an integer list. Okay, that's just an array of integers. And I know the length because it's Java. And this is my for loop and my for loop. So this, my bubble sort is n squared, right? And then all I'm doing is comparing j and j plus 1. Now I have a try catch because I have these. I have my thread in here. So I'm just going to go here. Temp is going to take my j, and then just the first number. And then if this j is greater than j plus 1, I swap. That's my swap. This is my swapping. And then I thread, right? So this is my nested loop, and this is my thing. If a number needs to bubble up, it's going to catch it because j and j plus 1. So I is going to be there, j is going to be there, and it's just going to move through the array and bubble that stuff up. And then here, I made a little driver because I hate static methods. I have a random, I'm just building random numbers inside of my list of 10. I'll probably cut that down to 8. Let's just do 8, it's easier to see. And then I have my length. Of course, I'm just generating random numbers, putting it in there. I have my unsorted list, printing out my unsorted list using my fancy loop. And then I call my bubble sort right here. Driver.BubbleSortList. List is the name of my array, and it goes up in here. Boop, bubble sorts, gets done with the bubble sort. Once it's done, I have a sorted list, okay? And there we go. So if I run this, make sure I'm running bubble sort, okay? Now, if we look, that's my thread slowing it down. This is my unsorted list. Well, 95 is going to start bubbling up each iteration. Then it comes back and it starts again. Well, 63 made the swap, but 75 is now bigger, so 75 bubbles up, and it stops there. Then I come down, 60 is going to swap with 63, or it catches 63, 63 moves up, and then 60 is going to move up, right? And then we have 34, so 23 and 34 swap, and then I have a sorted list. So these are my iterations. That's how many times it went through. I slowed it down. You can speed it up when you get this code. Play with your sleep thing if you want to. If you want to do it faster, if you want to make it bigger, see how long it takes. That's your bubble sort. All right. So bubble sort's there. And when you get a bunch of projects going in your package explorer, you can make sure that you're running the right ones, but your source file is going to be right here in Java. Okay, so that's going to bring it up. Oh, sorry. That's not your source file. Duh. Here you go. Beep. There you go. Okay, it's in your so source, and then that's your package. See, it's a little package. If you click on it, you're going to find your Java. So, I want to show you one more thing too. When you're going to add words, when you're going to add text files to your Java project, you want to make sure that you drop it into this part right here, okay? Can't do it. So you want to right click here, new, and then you can just go down in new file or new text file. And then if you put your text file in your source folder, okay, like that, you're going to run this and you're going to get your try catch error. It's going to say, oh, and I guess it gives it to me. So your source file is a good place. Oh, I'm running the wrong one. Ha! Let's run. Stop. That's my bad. Okay. So right now I have it in my source file, right? My text file is in my source file. And if you put it in your source file, if you right click on your source file and do new and new text file, here's what's going to happen. Let's run the by sort. Okay, file not found. And you're like, wait, file's right there. Well, it's in the wrong spot. I can't find it. It's not going to look there. So put it in your source file. Okay. Up here. Okay, you see that right up there? Words 2 is stupid. So we're going to delete that. But make sure that when you close your this, it's there. See, it can't be inside that. It's got to be on, you got to drop it into there, or you got to build it in that area. Once you do, it's going to go to my list. If I look at my words, I just got all these, I got 20 words, right? So here's what happens. Those are my unsorted words. I ran a bubble sort, sorted them. Now I'm going to run a binary search. So I'm going to look for echo. And echo is found at index 6. So how did that work? Well, let's go through the code really quick. Bubble sort's pretty simple. We've already done a bubble sort. This time we just did it with strings. Okay, this is a little more compact bubble sort because I don't have my try catch. But notice I have compare case. Exact same thing as my other bubble sort. It just is with a string. Okay, so if this compare case is greater than 0, now dot compare for Java is it'll do the like on the ASCII table, and it'll give you a value. And if the value is greater, it's 1. If it's less than, it's a 0. I mean, if they're equal. Okay, so if they're equal, it's 0. If they're not equal, it's 1. So you're comparing the actual object. So it checks to see if the object's equal. If both are equal, then it's a 0. If it's not equal, it's a 1. And that's how I can compare and alphabetize using this greater than 0. So if this is greater than that, it's going to give me a 1 as my output. Okay. Now I have my binary search. Binary search is easy. I'm just passing in my list and what I'm looking for. I call it target. Remember, left starts at 0, right is length minus 1. Okay, I'm just going to take my thing and be able to divide it in half. While left is less than or equal to right. This while loop just runs. Notice this is 2 for loops, n squared, bubble sort, 1 loop, n, except that I'm messing with my invariant, so it's a log n. Okay, and then it's going to say if my word is found in the middle, I'm done. If not, comparison is 0. If the comparison equals 0, I return my my index. If comparison is greater than 0, then my right, I go to the top. Okay. If what I'm looking for, if the word I'm looking for is less than what I'm less than a value in the middle, like if I'm looking for anchor, that's pretty much in the middle. Oh, I'm sorry, that's unsorted. If I'm looking for lantern, it's pretty much in the middle. Or let's go jungle, that's pretty more middle. If I hit jungle, boom, first try, it's right there. But if I'm looking for crimson, I'm going to look at this side. And then I'm going to divide this in half, and maybe I find it after 2 iterations. You can check how many iterations. That's kind of a fun thing to do. If I'm looking for puzzle, I start at jungle, and then I got to go to the top. Okay? And that's what the binary search does. Now I'm going to give this code to you. You can play with it. You can do your own words. Just go grab 20 words. Notice this is an array, so don't grab 25 words or you'll get an error. Okay? Because I wanted to sort the array. I didn't want to sort a list. Okay? So this is my try catch because I'm adding words, not text. This is so I can populate my list. List is just going to pop in. We did this in my last class if you were with me. File not found. We saw how that happens when your word's not in the right spot. Unsorted list just prints the unsorted list, calls the bubble sort. Now it's sorted. There's my sorted list. Now is my binary search, and it's going to, if I return a -1, right? If it's not -1, then I found it. If I return a -1, it's not found. All right, I'll put this in the comments, or however I'll figure out the YouTube thing. But there you go. That's a bubble sort, insertion sort, selection sort, binary search. N squared for the sorts, log n for the search. We'll get into linked lists on the next topic. Okay, this is just its starting point, but play with this code and write your own. Write an insertion sort. Use the code from the lecture and write an insertion sort. It'll be good for you. Okay. Great job. You guys are awesome. I'll see you when we do the other stuff. Bye.